Now in question 11, this organic question starts with a calculation, a moles calculation. We're given the equation for the complete combustion of methane. And we're now asked to calculate the mass of oxygen required to react exactly with 32 grams of methane. So whenever we're doing these questions, it's a good idea to write the formula triangle we're going to use in the corner, in the margin, or to one side. So we're using moles is equal to mass, that's an M, in grams, divided by the relative mass of the substances involved. Okay, so step one in this three-step calculation would be to work out the moles of the thing we have the most information about, and that would be actually the methane, because we have its mass. So we know the mass of this, we're looking for the mass of that. So step one is the moles of the known mass. So in the case it's moles of methane, N stands for moles, and that will be, as a function, moles is mass divided by relative mass. Take the mass from the question, 32 grams, divided by the relative mass of methane. Well, that's 12 is the relative mass of carbon, plus 1 times 4 for the 4 hydrogens, relative masses. So effectively, that's 32 divided by 16. Okay, so 32 divided by 16 equals 2 moles of methane present. That's the end of step one. Now, step two involves engaging with something called the molar ratio, the ratio of reacting moles in this equation. If we look at the equation, it seems to be implying that for methane to oxygen, there is a 2-to-1 ratio. For every 1 mole of methane reacting, it should react exactly with 2 moles worth of oxygen. So how do you get from 1 to 2? Well, you multiply by 2, okay? Don't forget, it's a function of getting from 1 to 2 moles is a multiplication of 2. So in reality, in this actual reaction we have, in terms of the actual quantities we don't have 1 mole of methane. We actually have 2 moles of methane. So if methane was 2, following the same molar ratio and that same function of multiplying by 2 to find out how much oxygen it will react with, 2 times 2 equals 4. We are going to have 4 moles of oxygen reacting with 2 moles of methane. So we've got 4 moles of oxygen reacting. Okay, that's the end of step 2. And just give yourself a bit of space, I'm going to do stage 3 down here. Okay, so we now know we have 4 moles of oxygen. So our solution would be, what mass of oxygen does this represent? Okay, the mass of O2. So the function is mass equals moles times relative mass. Mass equals moles times relative mass. Okay, we know the number of moles of oxygen is 4. We're going to times that by the relative mass of oxygen. Now, oxygen is 60 in the periodic table, times 2, because there are 2 oxygens present in the molecule of oxygen. Okay, so in other words, that's 4 times 32. Okay, and so 4 times 32 equals 128 grams worth of oxygen is required, and that is our answer. Okay, so we have 128 grams of oxygen. Okay, so it's a 3-step process: moles of the known mass of substance, molar ratio, and then mass of the unknown substance. And it's always the same 3 phases, if you like, for any molar calculation. Next, we have a complete combustion experiment. Okay, we've got a vacuum pump sucking the products of combustion through 2 apparatus, a U-tube exposed to some ice and some lime water in a conical flask. First thing is the products of combustion will be drawn into this iced water submerged U-tube. Explain why water collects in this U-tube area. This, whenever you're dealing with a sort of ice water being used in some sort of aspect of cooling and condensing, it's the 2 C's, okay, cooling and condensing. So I always call these the 2 C's for 2 marks answers. Okay, so why the water collects in U-tube? The water vapor, okay, the water vapor being produced from the complete combustion of methane is being, here's the 2 C's, cooled down and then subsequently condensed, second C, back to liquid water. Okay, that's why the water is collecting in the U-tube, probably just sitting at the bottom down there. Okay, next we have describe how anhydrous, without water, copper 2 sulfate, anhydrous salt, is used to test for the presence of water. Okay, so anhydrous copper sulfate, this is a white solid. Okay, now when you add water to anhydrous copper sulfate, it changes colour very distinctively to a vibrant bright blue. So the white solid anhydrous copper sulfate, if you add water to it, becomes a blue solid, and that is known as hydrated. It's different salt. It's hydrated copper to sulfate, and that is the distinctive colour change we're expecting to see to test for the presence of water in this experiment. Now, this last part of the question quite tricky because it's an explain command word rather than describe the change in appearance of lime water. Most of the time you're asked to describe the change in colour of lime water, but not to necessarily explain why that colour change is happening. A little bit more going on here, so I'm going to try and explain to you how you could do this. First of all, let's think about the chemistry of how lime water actually works. So lime water is saturated calcium hydroxide solution, okay? So an aqueous solution of calcium hydroxide right at the peak of solute dissolved in that volume of solvent. Okay, added to that is our bubbling through of carbon dioxide gas from the complete combustion process. What it's forming is calcium carbonate, effectively CaCO3, limestone, which is a white solid, and also some water as well. Now, the important thing is this stuff's being formed, calcium carbonate solid. So that will explain the observational change in the lime water, because the lime water will start off as a colourless solution, but as you bubble through bubble through carbon dioxide into that lime water, CO2 gas, what you're going to see is the lime water becoming opaque and turning cloudy. So lime water turns cloudy. And the reason for that is because we are forming insoluble CaCO3, calcium carbonate, solid, which is therefore a precipitate or precipitation reaction. And that is creating the colour change experienced in this lime water test. Okay, folks, well done for getting this far. We're entering the latter ends of the paper now, and in all GCSE papers, this tends to be the place where questions start to increase in complexity in certain areas and it begins to get a bit more tricky. Keep pushing, and let's see if we can get you to 100%, okay? So this question is about energetics and calorimetries. We've got an experiment where student is mixing 100 centimeters cubed of water in a polystyrene cup, a good insulating cup, and measuring the initial temperature of that water. They're then adding 8 grams of ammonium nitrate, which will dissolve in that water, and they're stirring at a uniform speed. And they're then recording the lowest temperature reached as that stirring goes on. Okay, you can see they've got here their values recorded. So you can see that the temperature went down from 20 degrees to 14.2 degrees. So use results in the experiment to explain what type of reaction taking place in this particular scenario, or type of process, maybe might have been a better word to say here, is going on in this with the ammonium nitrate and water. Well, what we have going on here is an endothermic process, okay? E-N-D-O-thermic. Endothermic. And how can I tell? Because, well, endothermic reactions or endothermic processes take in heat energy from their surroundings. Now, that would cause the surroundings to reduce in temperature. And in this case, the main surroundings of this experiment is the water itself. That's what's surrounding the chemicals. So the decrease in the temperature of the water is the giveaway, is the clue that is an endothermic process. So we've got endothermic processes taking in heat energy from the surroundings, and that is being signposted to us by the decreasing temperature of the surroundings, in this case the water, in the experiment itself. The next part of this question goes on to an MCAT, or Q equals mc/T question. Okay, we're being asked to show that the heat energy change in the reaction, known as Q, is about 2,400 joules worth of energy. Now, we're given the fact that 1 gram of water has a volume of 1 centimeter cubed, so density of water is 1 gram per centimeter cubed. We're also given the value 4.18 as the specific heat capacity of water. The amount of energy required to raise 1 gram of water by 1 degree centigrade, 4.18 joules worth of energy. So what we do is we recall and write down this formula for Q, the heat energy transferred in a reaction. Q equals M times C times delta T. M is the mass of water or of solutions in the question. C is the specific heat capacity of water in joules per gram per degree centigrade, which is 4.18 again. And delta T is the change in temperature in the reaction. So I've dragged this 100 grams of water from the previous question itself. So we've got 100 grams of water times 4.18, the specific heat capacity of water. And then we've got to look at the heat temperature change, in the reaction itself. So going back to our table, we can see we had 20 going down to 14.2. That's 5.8 degrees centigrade of change. Okay, so it's 100 times 4.18 times 5.8. And whack that in a calculator, what comes out is 2,424.4 joules of energy. So yeah, I mean, that's pretty close to 2,400 joules. So 2424.4. The final part of the question is then to calculate the enthalpy change per mole in kilojoules per mole. So we're getting kilojoules per mole, not in joules per mole, since units they've coded there, for the ammonium nitrate reacting or dissolving in the water. Okay, so I've dragged across again the 8 grams of ammonium nitrate from the question because I need that. Okay, and you've also been given the MR, the molecular mass, the relative molecular mass of ammonium nitrate as 80. That's going to be useful as well. So this is all useful information we're going to use in our approach. What I'm going to do is do a bit of dual coding and write the structure of the calculation. So our first step is going to be work out the moles of ammonium nitrate being used in the experiment. Okay, that again is going to use our formula triangle, moles equals mass over relative mass, in a second. That's step one. Once we've got the moles of ammonium nitrate, we're then going to do a Q divided by number of moles calculation to work out how much energy is being transferred per mole of reactant rather than just this minute amount of moles here. Before that, actually, I'm going to make that stage 3, actually, to be honest with you. So let's make that stage 3. Before that, actually, in stage 2 over here, I'm going to convert my joules value from the previous section into kilojoules to make it match up with the unit we're looking for. And that would be dividing by 1,000 to convert joules into kilojoules, because there are 1,000 joules in 1 kilojoule. And then finally, step 4 will be presenting our answer down here. Okay, so let's start with step 1, the moles of ammonium nitrate. So moles is equal to mass divided by relative mass. Okay, so we're going to take the mass from the question. Okay, so previously we had 8 grams of ammonium nitrate present, divided by the relative mass of ammonium nitrate given to us in the question as 80. So 8 divided by 80 equals 0.1 moles worth of ammonium nitrate present. So not a mole's worth, less than a mole's worth. We need to scale it up to as if we had a mole's worth of reactant in a second. So before that, converting joules into kilojoules, we're working in kilojoules, which is going to match up with what we're asked to present the answer in. So I'm going to take my answer from the previous section in joules, 2424.4, divided by 1,000 to convert it into kilojoules. That is 2.4244 kilojoules of energy being transferred by that much ammonium nitrate reacting. And now we're going to scale up to a mole's worth. Now, this Q value is important because it does respond to the nature of the experiment. If the reaction is exothermic and it's giving out thermal energy to its surroundings, this needs to be a negative Q value because it's giving out heat energy to surroundings. If, like in this particular example, it's an endothermic reaction, then this Q value has to be a positive number because it's taking in energy from the surroundings, and therefore it should be an increase in energy transfer. Energy transferred is going into the chemicals and increasing the energy of the chemicals themselves. So it's plus Q divided by moles. So we're going to do plus 2.4244, our Q value from the previous section, in kilojoules rather than joules, divided by the number of moles of reactant used, which is 0.1. Okay, and we do that, what's going to come out is, it's about like times by 10, isn't it? 24.244 kilojoules per mole. And remember, that's a positive number. And so you present your answer down here. And then the 4th mark is for including that sign. So let's put that in highlight as well. We've got to include the sign for the reaction taking place. So I have to put that plus there. Remember, that plus is important for that final mark. Plus 24.244 kilojoules per mole. So step 1, moles of reactant added. Okay. Step 2, convert joules into kilojoules from the previous section. Step 3, Q divided by mole to scale up to a mole's worth of reactant being used, and then present your answer with the right sign, depending whether Q was a positive or negative value, whether this was an exothermic reaction, negative, or endothermic, positive. Now, question 13 is going to be a rate of reaction question. A student uses the apparatus below to investigate the rate of reaction between magnesium and an excess, that's going to be important for later, of dilute hydrochloric acid. The method you use is as follows. A graduated beaker is used to pour 50 centimeters cubed of the acid of concentration 2 moles per liter into a conical flask. A piece of magnesium ribbon of exact mass 0.086 grams is added to the acid, and then they put a bung into the neck of the flask at that point. I'll come back to that point later on as well. Measure the total volume of gas collected every 10 seconds until the reaction stops. And that's where they've recorded their data here. Now, the first thing we're asked to do is to plot this data in a graph. Okay, and the graph paper is given to us in the question. So I'm going to quickly flip to that having been done, okay, to save the time of you guys watching me put crosses on. And I'll talk about both how you get marks for your graph and also how to draw the line of best fit as well. So I'll talk to you guys once I've done that. Right, when it comes to plotting a graph, the key thing is the precision of your points is vital. Okay, so make yourself familiar and make sure you understand the incrementally increasing scale you've been given. Make sure you understand what each square on the scale is doing. So for example, each square here is an increase of 2. Therefore, I can plot my points with great precision and accuracy. So for example, I'm looking for 51. I want to make sure that that is between 2 lines to represent an increase of 1 rather than 2. You will lose marks for every cross that is more than half a square away from where it actually should be. That means you're not being precise. Second thing is the curve of best fit. So a line of best fit generally goes straight through the majority of data points, but a curve of best fit wants to naturally curve through the data points provided, okay? That's a freehand drawing and smoothly curving and then plateauing at the end. Don't draw dot to dot with a ruler because that's not actually a curve and not what you're being asked to do. So you are absolutely at liberty to draw a smooth freehand curve with a pencil, not a pen. Now, the next part of the question is you're provided with different sets of data from other students. You're being asked to plot their data onto this graph as well to show how the curves would differ from the starting curve shown here. I'll draw those on now and explain how they have shifted or why they're different to the original curve. So here are the 2 curves now presented. Let's start off with Y. So Y, the conditions were half the mass of magnesium ribbon was given to us, but the same concentration of volume of the excess acid. So firstly, we're going to reduce half the amount of hydrogen gas compared to the original experiment because we are using half the amount of the limiting reagent reactant. But it's going to be a slightly slower reaction because that half the amount of magnesium ribbon is going to have a slightly smaller surface area than the original piece of magnesium ribbon. It's going to slightly affect, therefore slow down the rate of reaction. So our curve should start at the origin, generally be below the original curve, slightly less steep and therefore slower, and then ending up at 42 for half the amount of hydrogen gas generated compared to the original experiment. Now for curve Z, the parameters of the experiment are identical except for the fact that a slightly higher temperature is used. Now that will increase the rate of the chemical reaction, producing a steeper curve as we're generating the same amount of hydrogen gas but in a shorter space of time. So the curve should be starting at the origin, steeper than the original curve, and again plateauing at 84, finishing 84 because we're generating the same amount of product because we're using the same amount of limiting reactant, which is the magnesium ribbon. Okay, so the expected volume of gas that should be collected in that experiment is 86 centimeters cubed. This is the first experiment. So that's why the volume actually collected is less than this expected volume. So this is really a question focused on what could be going wrong with this particular experiment. Try and avoid generic statements about human error if you can, because this is more about this particular experiment. If we look at this particular experiment, where that source of error is most likely to come from is this stage right here, where you place the piece of magnesium in and then you put the bung into the neck of the vessel. At that point, gas can be escaping and not being collected before it's being measured, and so we're likely to get a little bit less volume collected than we should have got collected, and that's the key point, which is error is occurring. So the way we describe that is some gas, hydrogen gas, lost at that point when the bung is first being placed in the neck of the conical flask. So really do investigate the point in the experiment where that error could occur. The next part, again, is about the experiment. They used a graduated beaker, particularly low resolution, not very precise speed of apparatus, to measure the volume of dilute hydrochloric acid. Explain why it was not necessary to use a more precise measuring cylinder for this particular experiment. Now, the key word, again, going back to the original experiment, is that word here, excess. Okay, which means more than enough acid to go to completion. Therefore, we don't really need to worry about the exact volume because we've got more than enough present, even measured inaccurately or imprecisely, to get the job done. So since the acid is in excess or being added in excess, the exact volume of acid is not required. As long as it's enough to get the job done, and approximately 50 is good enough. Approx 50 centimeters cubed is sufficient. Okay, so that keyword was excess. Now, the ionic equation for the reaction between magnesium and hydrochloric acid is being shown below. Magnesium metal reacting with hydrogen ions from the acid, being donated from the acid to form magnesium ions and hydrogen gas. Use information in this equation to try and make reference to the equation and your knowledge of particle theory and collision theory to explain why the reaction would decrease during the experiments. As the experiments progressed over time, the rate of reaction will descend. But why? Well, it's because, think about it like this, guys. You've got that hydrogen ion concentration high at the start, lots of hydrogen ions reacting with your metal. But over time, of course, as they're being converted into product, the hydrogen ion concentration will be dropping. And so there's less hydrogen ions available to collide with the metal. Let's put that into words, shall we? So part one, or the first idea is that the concentration of the key reactant in hydrogen ions will be falling over time. Even though it's in excess, it will be falling. That will lead to there being less hydrogen ions in that set volume. Of water, in other words. There will be, therefore, fewer collisions occurring per second. Really important to include that unit time per second, per unit time passing. Do not say likely. Likelihood is banned. It's not about probability. This is about certainty. Fewer collisions per second, meaning proportionally, there will be fewer successful collisions per second. Okay? And all of that will result in the conclusive statement being, therefore, the rate of reaction will be descending. So really focus on the phrases that pay. Collisions per second and successful collisions per second. Vitally important for the vast majority of collision theory answers. So here we are entering what is known as the end game, as Dr. Strange would say, the last few questions in the paper. Let's have a look. This is a salt preparation question. A salt can be made by reacting an acid with an insoluble base, usually a metal oxide. A student has a sample of copper 2 oxide. See? The student uses this method. Put 50 centimeters cubed of dilute sulfuric acid into a beaker. Warm the acid with a Bunsen burner. Add a small amount of copper oxide to the warm acid and stir. Add further amounts of copper oxide until copper oxide is in excess. Almost gave away an answer there. Filter the mixture and obtain crystals from the filtrate. We'll expand upon stage 6 as part of this question, I think. But first of all, state why the acid is warmed in stage 2. Link it back to existing prior knowledge. When have you come across warming reactants being important? Hopefully in rates of reaction, okay? So it will increase the rate of reaction between the acid and the base. Okay, the student, then state how the student would know that the copper 2 oxide was definitely in excess in stage 4. Excess meaning more than enough to go to completion. There's some left over, in other words. So therefore, we'd probably expect some of that copper 2 oxide to remain at the bottom of the beaker. Or bottom of the... whatever vessel they're using. I'm going to say beaker, because I think it was a beaker. It was a beaker, yeah. beaker. So some of the copper 2 oxide is not reacting with the acid anymore, hasn't been converted into copper sulfate soluble product. It's just going to sit there as a black powder at the bottom of the beaker. State why the mixture is filtered in stage 5. Well, we've got an insoluble substance, insoluble reactant left over, which we don't want to keep. So we would be filtering to remove the insoluble copper 2 oxide left in excess. We don't want to keep that. That's going to affect the purity of our final product crystals. Okay, so remove those at stage 5. State the color of the filtrate obtained. Let's consider the reaction taking place. We've got copper 2 oxide reacting with sulfuric acid. So acid plus base forms a salt plus water. Our salt is going to be copper sulfate and water. So that's copper 2 sulfate. Okay, and that is a blue solution. So that's our answer, blue solution. All right, guys, a long answer question. Really going to be structured here. Okay, so I'm going to use pictorial diagrams to help me get across this idea really concisely and neatly. Describe how the student can obtain pure and dry sample of hydrated copper 2 sulfate, not anhydrous copper 2 sulfate. So we want blue crystals, not white powder, from the filtrate collected in stage 6. You've already done stages 1 to 6, carrying on from stages 1 to 6. Okay, so the first thing we want to do is to get a saturated solution. So step 1 is to set up a water bath with our little dish, evaporating basin, and we've got our copper sulfate solution, which is quite watery, quite dilute currently, and we're going to be heating that on a tripod probably. Okay, so that's our setup. The effect we're doing there is heating to evaporate some water, not all the water, from solution, from the filtrate. Let's call it the filtrate in this example. So we're going to be heating to evaporate some of the water, so heating gently on a water bath, evaporate some of the water, and our objective is to make a saturated solution. Okay, that's our first step. On to step 2 of our process. Now we have a saturated solution, which should look very different. It should have an evaporating basin with a very small puddle of our now saturated copper sulfate solution. So how do we prove that that is saturated? How do we prove it's a saturated solution? Well, that's where we come in with step 2. We take a cold glass rod. There it is. Label that cold glass rod. Now, what's the point in dipping a cold glass rod into a saturated solution? Well, what it should do is the cold glass rod should cool down the little region of the solution and it should form crystals. As the solubility of the solute decreases, so the cold glass rod should form crystals on the end dipped in the solution. And that is to prove we're at the saturation point. So it proves saturation, if you like. It proves we're at the right stage to carry on to the next step. So we've got ourselves we've proven we're at saturation. We move on to step 3. Okay, I'm going to do step 3 over here. Step 3 is then to, weirdly, cool the crystals down. Okay, or cool the filtrate down. Cool filtrate. Why we want to do that? We've just been heating it. Why are we cooling it down now? Well, cooling will encourage crystals to form and encourage crystallization. Okay, and that's because what's happening is you're going to have at lower temperatures, you're going to have a decrease in the solubility of the solute, the thing dissolved in the solution, and so crystals should form. Okay, the reason that works is, imagine this: if you had a hot cup of tea and you had sugar in that tea and you dissolved the sugar in that tea and you left your tea out for a while and came back to it and drank it, it's going to taste horrible firstly, but also you're going to have a ring of sugar crystals stuck at the bottom. That's because the solubility of the sugar in the hot tea has decreased as the tea's cooled down and you're crystallizing out the sugar. Same thing happening here with copper sulfate rather than sugar. On to step 4. So we've now got our crystals, but they're still a bit damp. They're sort of sitting in a little puddle like that. So you've got crystals forming, these lovely rhomboid crystals. They're still a bit damp, bit of water around as well. So we probably want to do, at this stage, step 4, another filtration, okay, just to collect the crystals. So another filtration step to collect crystals. Okay, collect those crystals. And then now we have some damp crystals. So we've got the lovely damp crystals. They're looking great, but they're still quite, they're still quite wet, not quite pure yet. So we probably want to do two things. Step 5, we want to wash them. Okay, gently wash them with some cold water, cold distilled water, just to remove any clinging particles. And then step 6 is dry them. And make sure you name the process you're going to use to dry them. So maybe a paper towel, dabbing a paper towel will be fine. Paper towel, dab, not dab as in the thing with your arms, but dab the paper like that. And then you've got your pure dry crystals. So 1, 2, 3, 4, 5, 6 ways of getting 5 marks. That should be enough to do the job. Brilliant. Almost there, folks. So F is another calculation. The overall equation is given to you here. In the experiment, the student completely reacts 9.54 grams of copper to oxide, okay, and show the maximum possible amount or mass of the hydrated crystals you should be able to form is about 30 grams. Again, proof of concept is the idea here. Again, the way we approach this is we know this one, we're looking for that one, okay. We're going to have to use our mole triangle again, so moles equals mass over relative mass. Let's put down some dual coding and some structure. Our first step is going to be working out the moles of the thing we know the mass of. That'll be the moles of copper oxide. Once we've got that, our second step will be something called the molar ratio again, and working out how many moles of hydrated copper sulfate that should be able to form. And our third step will be then working out the mass of that copper sulfate hydrate, okay, .5H2O. Okay, so start with this one over here. So moles equals mass divided by relative mass. We've been given, again, very usefully, some MRs, some molecular masses in the question to streamline our calculation, our working. Okay, so we've got 9.54 grams of copper to oxide divided by the relative mass of copper oxide given to us in the question as 79.5. So 9.54 grams divided by 79.5 equals 0.12 moles worth of copper oxide. Job done, part 1. Moving on to the molar ratio. According to this particular balanced equation, the ratio of copper oxide reacting to form the hydrated copper sulfate is literally 1 mole of it makes 1 mole of it. It's a 1-to-1 ratio, so therefore we can assume we are going to get 0.12 moles worth of the hydrate because we had 0.112 moles of the copper oxide. Okay, so it's the same 1-to-1 ratio, nothing to do there, just literally it's going to be the same. So bring that forward to here. How do we convert moles into mass? So mass equals, according to our triangle, moles times relative mass. Moles times relative mass. So we have over here, 0.12 times the relative mass of copper sulfate hydrate. Again, we've been given that to speed up to streamline things, so 249.5, and if we do that, we get 29.94. I think you'll agree. Oh, that's not a 9, that's a 2, Mr. Birch. 94. Right again, 29.94. There we go. Which is, I think you'll agree, pretty close, very close to 30 grams. Now, that's not necessarily an appropriate number of significant figures. When they say appropriate number, 9 times out of 10, they mean 3. They think that's an appropriate number. Fair enough. It's their exam paper. So we're going to just make sure we either round if it's above 5 or keep this to 3 sig figs. 1, 2, 3. Okay, no need to round because it's not above 5. So our appropriate number of sig figs is 29.9. Okay, 3 sig fig. I'm going to actually write to 3 sig fig. Perfect. Okay, so now finally, here we go. Let's work out our percentage yield. I'm going to use this number here for simplicity. Okay, so percentage yield calculations are always the same in terms of formula. It is the actual yield given to you divided by the theoretical yield you have calculated through your molar calculations times 100 to convert it from the value it is in terms of a fraction into a percentage, a value out of 100. Okay, so we're going to have 23.92 is our actual yield. We're going to take 29.9 as our theoretical yield given from our previous section. We could even do 29.94 if we're being really precise, Frank. It's going to give basically the same answer, isn't it? Times 100 to convert to percentage, and you're getting about 79.89 percent, which is pretty much 79.9%. You could even round it to 80.0% in theory. I'm going to leave it in 79.9%. And that's our answer. Okay, so we're getting a 79.9% yield, pretty good yield, frankly. Not too bad at all. The final question. Woo! Okay, let's do this, people. So, hydrated ammonium iron 3 sulfate is a violet solid with the formula NH42SO4 dot Fe2 SO4 brackets 3x dot x H2O. Quite a complex formula. Don't worry, just break it into pieces. I can see that if you break it into pieces, we've got ammonium ions in there, NH4 plus ions. We've got sulfate ions, SO4 2 minus ions. We've got iron 3 plus ions. How can I say 3 plus? Because this section here is iron sulfate. You've got 3 sulfates to every 2 ions. That's 3 times minus 2, giving you minus 6, meaning that these are 2 plus 3s to balance out the charge of that. So we definitely have iron 3 plus ions. And that's kind of it, because the rest of it's just water, isn't it? And these are sulfate ions as well. So those are the 3 ions in play. Effectively, you've got ammonium ions, sulfate ions, and iron 3 plus ions. Dissolve the solid in water and add acidified barium chloride solution. And what will you form? Okay, so acidified barium acidified barium chloride, sorry, is the test for sulfate ions. Okay, so what happens when you add acidified barium chloride is the barium ions, which are Ba2 plus ions aqueous, react and interact with the sulfate ions SO4 2 minus aqueous to form a solid substance, which is barium sulfate, incredibly insoluble, white in color. So what you see is a white solid, or a white precipitate. And that's our observation number 1. Now we're going to dissolve the solid in water and add a bit of sodium hydroxide solution to the solution and see what happens. Again, what's going to happen? Well, this time this is testing for the iron ions. So the iron ions, the Fe3 plus ions, which are currently aqueous, will interact and react with the hydroxide ions added, 3 of them, because each one is minus 1. And what it will form is the compound known as iron 3 hydroxide, FeOH. Solid. Now again, that's a solid, so it's a precipitation reaction, and what we're going to see is a red-brown precipitate, or a red-brown solid, and that's your observation. Okay, 2 out of 3. Now finally, we could add some sodium dioxide solution to the solid and warm the mixture. That's different, so just keep in mind on that. And then test the gas given off with some moist universal indicator paper. So what's going on here? Different kind of reaction again. So this is a bit different. The ammonium ions are acidic in nature, and what you're adding is hydroxide ions, which are alkali in nature. So the acid reacts with the alkali to form ammonia gas and water. Now that's the important substance coming off in terms of the gas being generated. That's what we're warming for, to try and get that gas generated. And that gas will interact with this universal indicator paper, and because it's alkali, the universal indicator paper will go from its natural color of green at currently neutral conditions to a purple color, because this is an alkali substance. Fabulous. 3 marks in the bag. Let's move on. Now the student needs to find X in the formula of this huge formula here. Okay, they use this following apparatus: hydrated ammonium iron 3 sulfate. Okay, they heated it, and they are then passing this through here in ice. Okay, so the water's condensing, cooling, condensing again, and we're given this as our final process. Okay, there's the end result. Now the last bit's going to be a calculation. It's going to be quite in depth, but we'll get through this and get our 100%. So our final step is to use this table of data presented to us to work out these 3 last little bits. First of all, we're asked to calculate the mass of the anhydrous compound being produced by the heating. Okay, to do that, we take the mass of the anhydrous compound itself from the experiment, which is this one here. This is when it's had the water driven off, which is 28.69. Remember, that's the mass of the anhydrous form without the water. It's been driven off. And we take away from that the mass of the empty tube to find out just what the compound itself weighs, and not the tube as well. We're going to take away 22.04. Remember, that's just the mass of the glass tube itself. So it's the compound and the tube together minus the mass of just the tube on its own. And that will give us our answer, which comes out as 6.65 grams. Now, second part of the question is calculate the mass of water produced, or how much water is what mass of water is being driven off from the hydrated form up here. So again, what we do is we write down the mass of the hydrated form of the compound, 34.09. Remember, that's the hydrated form with the water. We take away the mass of the anhydrous form. Remember, that's with tube as well. Take away the mass of the anhydrous form with the tube, which is 28.69. Remember, that's the mass of the compound once the water has been driven off. That's called the anhydrous form. And that will just tell us how much water was driven off. The difference in these numbers is the amount of water being driven off, and that is 5.4 grams. So that's the amount of water being driven off, and that, don't need the grams there, it's already given to you. That's the amount of water being driven off, and that is the mass of just the anhydrous form of the compound once the water's gone. And then it says, calculate the value of X in this formula for the hydrate here. Okay, so that is what we call hydrated salt formula calculation, but I treat this kind of like empirical formula, frankly. So what we're going to do is literally just lay this out like an empirical formula, and we'll do that now. So we're going to have the anhydrous form of the compound over here, SO4.Fe2SO43, okay, and that's one side, and then we're going to have water, H2O, over here. We're going to do the standard empirical formula layout. So first of all, we're going to write down the mass from the question. For this, 6.65 is the amount of the anhydrous compound we've got, and here 5.4 is the mass of water driven off. Okay, we're then going to write down the not atomic masses, but the molecular masses. Okay, how much relative mass the molecules have. So this one has given to us in the question 532 is the mass of this compound, the anhydrous form, and water is 18. So 6.65, we're going to divide that by the relative mass of the whole molecule to work out moles. 532 is going to go there from here. 18 is going to go there. That's just the molecular mass of the substance involved. Next we're going to work out is moles. Remember, moles is the mass divided by relative mass. So 6.65 grams divided by 532 and 5.4 grams divided by 18. It's looking very similar to empirical formula. If we do that, what we get is 0.0125 and we get 0.3 moles, okay? Then we're going to do down here the molar ratio, divide both of those by whichever one's the smallest to work out the magnitude of one compared to the other in terms of size, which number is bigger and by how much. So 0.0125 is definitely the smallest number, so divided by itself would of course give us 1. Now 0.3 divided by 0.0125 gives us a huge number, gives us 24. But that's our answer, okay? So what's the value of X? 24. So this number here in this formula is 24. There's 24 waters as part of this total formula. So it's kind of like a hydrated salt formula is kind of like a big version, a sort of extended version of an empirical formula calculation. But it's exactly the same method, just remembering that this isn't elements, it's actually compounds. And that brings us to the end of that IGCSE paper, Edexcel paper. Amazing sticking through it all the way to the end, guys, and I really hope it was helpful. Please do have a go at the paper, download it, look at the link in the video for that, and have a go work through it with me so you can get this all done yourselves. And if you need a deeper dive into certain areas, because this was quite a quick run through. If you want to go into empirical form in more detail, check out the channel, go find the video on that particular topic and do that deep dive and get the information you need. This was just helping you guys to get 100% in a paper like this. I hope you'll join me for others in this series where I go through other papers in GCSE and A-level, hopefully in the future as well, to show you how to get 100% in all kinds of different chemistry contexts. But as always, guys, I wish you the very best of luck with everything coming up for you in terms of mocks, in terms of real exams in particular. I hope this really helps you to nail those exams and get the 9s you're looking for. So I really want to help as many students as possible to maximise their potentials and to really have a good time in chemistry. All it stands for me to say is thanks for listening, guys, and take care. Bye now.